Welcome to this session of digital electronics. We are currently dealing with the self-starting counters and we have completed one question on how to find whether a counter is self-starting or not. So here we have ended the previous session how to check whether the counter is self-starting. So to do that, we take up all possible cases, all possible states and see whether we'll get stuck anywhere or not. Okay, we'll extend from here the concept of self-starting counters. Okay, see here. So when can we say whether a counter is self-starting? Okay, we can say if the counter starts in a unused state. If it starts in a unused state, it comes out and goes into user state. Okay, if it happens, then we'll call that counter as self-starting counter. Here in the previous question, the sequence goes like this: 1, then 2, then 3. From 3 again it comes to 1. That means the zero state is unused here. How many states are possible? There are two D flip-flops, that is 2 flip-flop means 2 Qs will be there. So 2 bits are possible. So with 2 bits, it can be 0, 0, 0, 1, 1, 0, 1, 1. That means it is 0, 1, 2, 3. So these are the possible states, out of which our counter is going through 1, 2, 3. That means 0 is not used at all. Okay, 0 is not used at all. But even if the counter goes into 0, then it comes to 1 and the cycle repeats. If we draw the state diagram in terms of binary, then first one is 1, that is 0, 1. 1 is represented in binary as 0, 1. Then 2 is represented as 1, 0. Then 3 is represented as 1, 1. So from 0, 1 it goes to 1, 0. From 1, 0 to 1, 1. From 1, 1 to 0, 1. And 0, 0 is unused state where even though you get 0, 0, then it immediately jumps to 1, 0. So this is unused state and remaining ones are used states. Okay, now let us take one case where we have a design of flip-flop. Let us take it as case 1. So this is case 1. So I will take 2 flip-flop here. One is this, second one is this. Okay, so both are D flip-flops. First one is D1, this is D2. So output of first one is Q1. Here it will be Q2. And we supply same clock to both of them. Suppose say this is the clock. Now we connect. Suppose let us see it as, let us take it as D0 and Q0. So we connect Q1 to D0. Okay. Then Q1 we take it here and Q0 we take from here. Okay. Both of these are inputs to a OR gate and it is NOR gate. So this is given to D1. So if you carefully observe this, what will be the next state? The next state, that is Q1 plus, will be D1, is it not? Sorry, Q1 plus will be D1. Whatever the value will be there in D flip flop at D, the same will be replicated in the Q1. So D1 is what? You see here, what is D1? D1 is NOR gate of Q1 and Q0. That is Q0 plus Q1 whole bar is nothing but Q1 plus. Similarly, what is Q0 plus? Q0 plus is D0. Then D0 is Q1. Okay. So these two equations are necessary for us to draw the table. So if you take these two equations, suppose let me take these two. Okay. Now, if you try to construct a table using this, I say I will take Q1, Q0, get then Q1 plus, Q0 plus. Let us take this, take all the possible state to check whether this is self-starting counter or not. So what are the possible cases for Q1 and Q0? That is present state. This is present state and this will be next state. So possible cases are 0, 0, 0, 1, 1, 0 and 1, 1. Using these two equations, this one and this one, let us see what is Q1 plus and Q0 plus. Q1 plus is Q0 plus Q1 whole bar, that is 0 plus 0 whole bar, that is 1. And Q0 plus is Q1, it is 0. So Q0 plus follows Q1, so we'll directly write this as 0, 0, 1, 1. And Q1 plus is NOR gate of Q0 plus Q0 and Q1. That is 0 plus 1 is 1, so it will be 0. Remaining will be 0. That means if the state is 0, 0, what will be the next state? Next state will be 1, 0. See from this table, the state is 0, 0, the next state will be 1, 0. Next 1, 0, next state will be 0, 1. So from 1, 0, next state will be 0, 1. So from 0, 1, next state will be 0, 0. So from 0, 1, next state will be 0, 0. That means this is a closed mod 3 counter. But what about 1, 1? 1, 1, if it occurs by mistake, it goes into 0, 1. That means here you can write like this. If 1, 1 occurs, then it goes to 0, 1. This 1, 1 is unused state. This 1, 1 is unused state. If it comes into unused state, it again goes into used states. That is, what you call this, self-starting counter or not self-starting counter? Yes, this is self-starting counter. Okay. Now let us take one more case. Let us take case 2. In case 2, I have a different combination of circuit. Here also I will take the same D flip-flops. Here there is one D flip-flop. The same I will copy. Okay. Now there are two flip-flop here. Let us take this as a D1 flip-flop and this is D0 flip-flop. The output is Q1 here and output will be Q0 here. And both are supplied to same clock only. Clocks are same. Now I take Q1 and I connect it to D0. So I take Q1 and connect it to D0, and I take Q1 and Q0 and connect it to an XOR gate, and connect that XOR gate to D1, let us say. Now this is a different combination. This we have not seen earlier. Now now what is Q1 plus? That is what is the Q1 plus in this case? Q1 plus is nothing but D1. What is D1? D1 is XOR gate of Q0 XOR Q1. Okay. And Q2, sorry, Q0 plus is D0. What is D0? D0 is directly equal to Q1. That means using these two equations, I'm going to draw a state table. Sorry, if I take Q1, Q0, and next state as Q1 plus and Q0 plus. If I take like this, then what are the four possible cases? 0, 0, 0, 1, 1, 0, and 1, 1. If it is 0, 0, then Q1 plus and Q0 plus you see. So Q0 plus is same as Q1. So I will repeat 0, 0, 1, 1 here. And Q1 plus, if you see this equation, Q0 XOR with Q1. So 0 XOR 0 is 0. And 1 XOR 1 is 0. Remaining two cases, it is 1, 1. That means if it is 0, 0, then it remains in 0, 0 state. The next state will be NS stands for next state, PS stands for present state. So next state will be 0, 0 itself. That means 0, 0. The next state will again it will be 0, 0. And if it is 0, 1, next state will be 1, 0, 1, 0. 1, 0, next state will be 1, 1. And if it is 1, 1, next state will be 0, 1. So this is a mod 3 counter again. What is the sequence of this counter? This stands for decimal 1, this stands for 2, and this stands for 3. So it is 1, then 2, then 3, again it goes to 1. So like this the counter operates. But what about the unused state 0, 0? The unused state, this is unused state. If any unused state occurs, it will get locked out. This phenomenon is known as lockout. So it gets locked out in the same 0, 0, and the counter cannot resume on its own. So it is not a what? It's not a self-starting counter. It is not a self-starting counter. Okay. Now, so we have seen the examples of what is a self-starting counter and what is not a self-starting counter. Let us see some more examples. Suppose let us say I have a sequence 0, then 4, then 6, then 7, then 3. From 3 it goes to 1, and from 1 it goes to 0. How many states are there? 1, 2, 3, 4, 5, 6. So as there are 6 different states, this is a mod 6 counter. Here you can observe that suppose if you have a binary system, to represent the greatest digit here you need 3 bits, 1, 1, 1, right? So starting from 0, 0, 0, it goes up to 1, 1, 1. 0, 0, 0 stands for 0, then 1, then 2, so on up to 7. So out of this 0 to 7, only these digits are present in the circuit, which I have shown here. What about the remaining digits? Like there is no digit 2 here. There is no uh, 1 0 1 2 is not there. 3 4 5 is not there. So 2 and 5 are missing here. That means 2 and 5 are unused state. If 2 occurs, if it goes to 5, if 5 occurs, then if it goes to 2, I'm just saying an example. If it happens like this, then this is also a lockout condition. So 2 and 5 are unused state. Only if in the above this particular scenario, there is a mod 6 counter, and when 2 or 5 occurs, interchangingly the other digit will occur. So this is not a self-starting counter. Then let me say 0, then 4, 6, 7, 3, 1, 0. So from 5 it goes to 6, from 2 it goes to 3. So this is a self-starting counter or not? Here also 2 and 5 are unused, but this is a mod 6 counter. Though 2 and 5 are unused, occurrence of any of the state 2 or 5 will not lock out the counter. Immediately it will go into the 6 or 3, and the counter continues. So this is what? This is a self-starting counter. So next, let us take more example. Suppose the states are like this. First one is 0, 4, 6, 7, 3, and 3 to 1, and from 1 it again goes to 0. And there are two here also, there are two digits which are missing, that is 2 and 5 are missing. So starting from 0, 1, 2, 3, so on 7, 2 and 5 are missing in this case. So 2 and 5 are unused state. But if 2 and 5 are arranged like this, so if 2 occurs, then it goes to 0. If 5 occurs, it goes to 7. If such kind of case occurs, then this is a self-starting counter again. And there is one more scenario also. Suppose 2 and 5 are interlinked like this. So there is this another example. So suppose there is 0, then 4, then 6, then 7, then 3. Then from 3 it is 1, from 1 it is 0. So when 2 occurs, let it goes to 5, and 5 goes to 3. So 2 and 5 are unused states here, and this is a mod 6 counter. Is it a self-starting counter or not? Though so this is a self-starting counter. One unused state went into another unused state, but the unused state 5 goes into a used state, so it will start on its own. So this is also a self-starting counter. Okay. Now let us try to design how to design a counter. Let us see now. So suppose I want a counter which counts from 0, 4, 6, 7, 3, 1, and again 1 goes to 0. So this is what? This is a mod 6 counter. We have to design a counter. So this is one. Yes. We have to design a counter which counts in this given sequence. Now to do that, let me minimize this. See, so this is a mod 6 counter. That means 3 bits are required. Yes or no? Up to 7 it is there, so 3 bits are definitely required. As 3 bits are required, we can understand that 3 flip-flops are required. Okay, 3 flip-flops are required. So I will have the states Q2, Q1, Q0. This is the present states. Then next states there will be what? Q2 plus, Q1 plus, and Q0 plus. Okay. And based on that, we have to design D2, D1, D0. This we have seen in the last session how to design that. So here we will take based on the cycle given. So this is the sequence that is required. Let me take this sequence. Yeah, let us see that sequence and fill here. So the first one is 0, 0, 0, 0. If it is 0, it goes into 4. 4 is represented in the binary as 1, 0, 0. So 1, 0, 0, if it is there, it goes to which one? It goes to 6. So 6 means 1, 1, 0. If it is 1, 1, 0, then it goes to 7, 1, 1, 1. If it is 1, 1, 1, it goes to 3. 3 is 0, 1, 1. If it is 3, 0, 1, 1, then it goes to what? 2. Sorry, not 2. It is 1 only. 1 is represented as 0, 0, 1. Okay. If it is 1 again, it goes to 0, 0, 0, 0. Okay. In this scenario, what are the unused states here? Obviously, again, 2 and 5 are unused states. Okay. So if they ask us just design a counter, you need not consider the unused states. You directly write the unused states. So what will you do? Let me minimize this. Here, see here, the unused states here are 2 and 5. 2 is represented as 0, 1, 0 and 5 as 1, 0, 1. So need not worry about what these two states. You can directly put whatever the next state it will be, it is okay. So because they didn't ask anything about self-starting or not self-starting. They have just said given the sequence, okay, given the sequence like this, design a counter. That's what they have asked. So you need not worry about the unused states. So here you use K-map here, then individually solve what is D2, then D1 and D0. This kind of procedure we have done in the previous session. We here also will do like that one, like that. So this is the way in which, so if D2, D1, D0 is found, we will find a sequential circuit, and that's how we will do it. Suppose same question they have asked with counter, with self-starting facility. So if same question they have asked to design a self-starting counter, with the sequence given below. So the same sequence that we have seen earlier. Yeah, this is the sequence. Okay, so this sequence, with this sequence, if I have to design a self-starting counter, then what we have to do here, self-starting means if unused state occurs, we should not neglect them. We should connect them to any other user states. Okay, so the remaining part of the table remains just like this. Okay, see here. So in this particular, so same question is given, but with they have asked with uh, self-starting. So then what we have to do? Whenever unused state occurs, we have to take care of them by redirecting them to any of the user states. You can see any of the user states. So all these are user states. All these are user states. So you can redirect whatever the unused state that occurred here. You can redirect to any of the user states. So let us say I have redirected 0102 000, then 1012 001. Here in this place you can put any values. You can put 100, then 011 you can put, so that they will become user states. So here we have taken these values. So based on this we will use the k-map and solve d2 d1 d0, and finally we will figure out what is the design of the circuit. Okay, then we will design the circuit. That means what you have actually done here, the unused states we didn't take care in the previous question, but in this question we took care the unused state will go into used states. Okay, in exam if they don't ask you to about any self starting, if they just ask you about design a counter with the following sequence like this, then don't do any unnecessary task, unnecessary action you need not do. You can directly take the other next state as don't cares. If they asked especially that they want a self starting counter, then you can direct, if any of the unused states occur, you can direct it to use states. Okay, that's how you will do this kind of questions. Now let us see this question. A combination circuit is given here which is connected to a JK flip flop, and the question is asked like this: the value of J and K such that above circuit works as XY flip flop R. The state diagram is shown above. So this is the state diagram that they are giving us. So this is the state diagram, and this is a JK flip flop, and this is a combinational circuit. So they are asking the value of J and K or what. Hmm? So to solve this question, we should know what is JK flip flop. So first of all, let us minimize this. Okay, let us start. So first, what is JK flip flop? So JK flip flop is a very important concept. So concept that we are learning here is going to learn here is JK flip flop. So JK flip flop is designated like this. Yeah, see here, JK flip-flop has J, then K, then Q, Q bar. Obviously, there will be a clock. A clock will be there. So these are the JK are the inputs and Q and Q dash are the outputs. So if we see the state table for JK flip-flop, state table. Forget about the question. We are learning about JK flip-flop. So state table for JK flip-flop. So state table means inputs will write here, and what is an output, we'll write it as Q plus. This is the next state. Okay, now the four possibilities are 0 0 0 1 1 0 and 1 1. So the state table of JK flip-flop shows like this. So if the J and K are 0 and 0, then the same value remains. That is, this is known as hold mode. If it is 0 and 1, then output will be 0 in the next state. That is reset. Reset means 0. Then if J is 1 and K is 0, then the output will be 1. That is set. If J is 1 and K is 1, then the output will toggle. This is the state table for the JK flip-flop. If you see the state diagram for JK flip-flop, let us see. So first, what is the state? Let us take 0 0. Suppose Q is equal to 0, let us take here. Then Q is equal to 1, let us take here. Now, if it is 0, when it comes to 0, Q is equal to 0. So either if previous bit is 0 and J and K are zeros, so then if Q is equal to 0, then one condition is if J is equal to 0, K is equal to 0, or what is one more condition to get 0 irrespective of what is Q? If K is equal to 0 and if J is equal to 0 and K is equal to 1. In that cases, the Q goes to 0. Then 0 0 you get the same value, then 0 1 you get reset, then 1 0. Suppose the value is at Q is equal to 0. If you get 1 0, then you will have what? Set, that is 1. So hey, how we'll go here? So this is Q is equal to 0 is the state, and to go to Q is equal to 1, then see. So let us do like this. Let us do, there are two states, Q is equal to 0 and Q is equal to 1. If see this table here, J and K and next state are given. If J and K are 0 0, then what about the next state? It will same the same value. It will hold the same value. So J is equal to 0, K is equal to 0 is here. If J and K are 0 1, then also it will remain in the 0 state, that is reset state. So we have taken J is equal to 0, K is equal to 1 here. Then if it is 1 0, then it will go to set. That means Q is equal to 0. If the input J and K are 1 and 0, then it goes to set. If it is 1 1, then what happens? If it is 1 1, then toggle. That means same 1 1 also will come here. Okay, we have completed one stage. Similarly, if Q is equal to 1, let us start from here. If q is equal to 1 and j is equal to 0 and k is equal to 0, the next state will be same. Can I write like this? Or I can write in a normal fashion only. J is equal to 0, k is equal to 0. And if set is there, set means j is equal to 1 and k is equal to 0. So if j is equal to 1 and k is equal to 0, then also the previous state is 1 and now also it remains at 1. Sorry, here k is equal to 0. So two cases are over. This over and this 1 0 is also over. If the inputs are 0 1, this one inputs are 0 1, then reset. So for 0 1 it got reset. Then if inputs are 1 1, then it toggles. So here 1 1 comes again. So this is the state diagram for the JK flip-flop. So same state diagram can be represented in one more form also. See here carefully. Same state diagram can be represented like this. So there is Q is equal to 0 and there is Q is equal to 1 and Q is equal to 0 remains at Q is equal to 0 for two cases, that is 0 0 and 0 1. So that means irrespective of what is the second digit, Kitas don't care. So irrespective of what is the second digit, if the first digit is 0, then Q will remain in 0. If J is 0, then Q will remain in 0. Next, 1 0 and 1 1. So this is also so J is 1 here, irrespective of what is X, then J is 1 here. If it is Q is equal to 1 and J, K are 0 0, so and J, if J is equal to 1, K is equal to 0. So you can write here don't care 0, because J is equal to 0 or J is equal to 1, the K will remain 0 and the output again comes to Q is equal to 1. Okay, now now we are going to see the excitation table for JK flip-flop. Excitation table. Excitation table means we will take the output and we will evaluate the input. Now this is very important for the competitive exams. So excitation table, what are the four possible states? 0 0 0 1 1 0 1 1. So that if we take the J and K states, then for 0 0, that is present state is 0, next state is 0. What is the possible case? 0x, right? This 0x I am 0x I am saying from this particular diagram. So from that table you can say JK are 0 and X, don't care. If the present state is 0, next state is 1, then what is the case? If present state is 0 and next state is 1, you can see from here. So this is missing. This is what? 0 1 1 1. So this is x1. So if present state is 0, next state is 1, then possible scenario is x1. Sorry. So 0 to 1. 0 to 1 possible scenario is 1x. Sorry. So from 0 to 1, see here 1 0 and 1 1. That means 1x. So this is not x1, this is 1x, and this is x1. Okay, now it is good. So now using this diagram, I can write j and k states. If it is 0 and next one is also 0, then possible case is 0x. If it is 0 and next state is 1, possible case is 1x. If it is 1 and next state is 0, then x1. And finally, if it is 1 and next state is also 1, then don't care 0. This is the excitation table for the JK flip-flop. Now, if I try to draw, try to derive the present question. So present question, we are going to that now. So suppose in the question they have asked x and y, and present state they have given, and next state also they have given, and we have j and k flip-flops. So xy are here, q dash are here, and jk are here. Now, so if given scenario, we can note it here. So in the question it is given, this is the given state diagram. So let us bring it here also. Here x and y are the inputs to j and k. So all the possible cases for x, y and q are, so first one is 0 0 0, then 0 0 1, like that it goes on. If you draw it, if I draw it, if I write it in one shot, it will be 0 0, sorry, it will be 0 1 0 1 0 1 0 1, then 0 0 1 1 0 0 1 1, then 0 0 0 0 1 1 1 1. So these are the possible cases. So from the state diagram is given here, if the value is q, and the next state that we have to get is what? So x and y should be 0 0. Then next state will be, so if x and y are 0 0, then present state is 0. Then next state will be the same 0. Similarly, going on filling like this, you will get x and y are 0 0. Then present state is 1. The next state will also be 1. So if you go on filling like this, then you'll get 1 0, then 1 0 0 1. So jk values for this is consider only q and q dash. So jk values will be from the previous excitation table 0x, then x0, then 1x, then x1, it will be again 1x, x1, 0x, and x0. So don't cares and zeros are present here. So this is minterm 1, minterm 2, 1, minterm 2, 3, 4, 5, 6, and 7. Okay. Now let me minimize this for convenience. So from this, if I draw the K-map for X, Y, and Q, and we have to derive what is J from this. So if you do like that, how will be K-map look like? So one is this, then inside there will be lines. Okay. Now this is X, and this is Y and Q. So X can be 0 and 1. So YQ can be 0, 0, 0, 1, 1, 1, and 1, 0. So that means 0, 1, 2, 3, 4, 5, sorry. So 0, 1, 2, 3, 4, 5, 6, and 7. So from J, you can see that when it is 1, so here it is 1. That means minterm 2 and minterm 4. And in the remaining minterms, it is 1, 3, 5, 7. It is XOR. Sorry, it is, no, don't care. So 1, 3, 5, 7. So how can we simplify this? So x and 1 one term and x and 1 other term. So J is, what can you write? Can be written as xy bar plus x bar y. So this is xy bar and this is x bar y. So J we have written like this. Similarly, let us write for K also. So this again x, y, and q. This 0, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0. Here we will get ones at m3, m5. So 3 and 5. And x at, that is the don't case at 0, 2, 4, 6. So that is 0, 1, 2, 4, 5, 6. So these are the terms. So here we can again combine them, and I can write the k as x XOR y, x XOR y. So we have got j also is also x XOR y. So j and k are same, that is x XOR y. So in the given question, what is the combination circuit to be included here? So what is this combination circuit? This combination circuit is nothing but XOR gate. And same supply, this is the, these both inputs are, outputs are same, and the resultant circuit we can draw like this. So let us see how to draw the resultant circuit. So x and y are there, both are passed through the XOR gate, and it is supplied to the JK flip-flop to get the desired output. So this J, this is K. So same input goes to K also. So this is Q, this is Q dash. So this is the required XY flip-flop that is asked in the question. So we have completed this question. Now we will stop here and we will see the remaining things in the next session.